Hello everyone. So in this lecture, I'm gonna first talk about stability concept in these kind of fluid flows, and then we are gonna briefly discuss pressure variation in a fluid with a rigid body motion, and then we will solve one simple example of that, and after that, this will be the end of chapter 2, and we are going to move to the next chapter by introducing Bernoulli equation in chapter 3. Okay, so let's get started. So first I want to give you a overall idea about stability, the stability concept. Okay, so let me see. Okay, we have, let me just talk about stable and unstable equilibrium. So imagine these two situations where we have like a ball or a circle that we put here. So imagine we have a ball here and then we put it here. And then we have the same ball here. Okay, so let's first investigate the one on the left. What's going to happen to the ball on the left? The ball on the left is going to move and it will go some around, like it goes here, comes back, comes here, and then finally it will reach to an equilibrium. And the equilibrium point of that is here, right? It will reach to an equilibrium here. Okay. So wherever you put the ball, like if you put it here, if you put it, I don't know, like, let me just extend this a little bit. If you put it here, if you put it here, wherever you put the ball, after some going and coming back forward, and finally it will reach to an equilibrium at this point, right? So this kind of equilibrium, we call it stable equilibrium, and that means that when the ball or when the object is displaced, it returns to its equilibrium position. So if you had a ball here originally and then you move it here, or you move it like here, anywhere you move it, it's gonna come back and return to its original position. Okay, so this is what we call stable equilibrium. Okay, so let me just underline that, stable equilibrium. And what if we have a ball here? If you have a ball here and just displace it a little bit to the left or right, it's not gonna stay there, right? So if, for example, you just displace it a little bit here, then it's gonna start moving and falling down, right? It's gonna start moving here. So for these situations, we call this kind of equilibrium as unstable equilibrium. So unstable, we have an unstable equilibrium. What does that mean? Means that when displaced, it moves to a new equilibrium position. So it doesn't return to its original equilibrium position, and it will go to a new equilibrium position. For example, if you have something like this, and then move it a little bit to the right, it can go and get to an equilibrium, to a new equilibrium position here. Okay, so that is what we call an unstable equilibrium. Okay, we have the same concept in fluids, in immersed bodies inside a fluid. Okay, so let's look at that. So immersed body, so imagine we have some water up to here. Okay. Also, we have some water here. So, and then we have an object inside, an immersed body object inside this water. Okay, so now what I'm gonna do is I have a heavy object at the bottom of it. So you have this object is not symmetrical, so this object has a heavy part at the bottom of it. So here we say heavy material. Okay, so this heavy material brings the center of gravity of this object to, so if this is the center of area, right, the center of gravity is going to be below that because of this heavy object. So let me just show it. So this is going to be the center of gravity, and I show this with, and the weight of it I show it with W. Okay, and then we have a buoyant force that acts to the center of area. So let me show that with this. This is the buoyancy force that acts on this object. So what's going to happen? Is this a stable equilibrium or an unstable equilibrium? So if it is a stable equilibrium, if we displace it, then it has to come back to its original equilibrium position, which is this one, right? So let's displace it and see what happens. So if we displace it a little bit, let's say to the right, so we have the center of gravity is going to be here, and then we have center of area here. So the buoyancy force is always an upward force, directed vertically upward. So it's going to be toward the top. And then the gravitational force is always also a vertical force towards the bottom. So we have this W, and then we have this FP. So as you see, if you calculate the moment around the center of this object, which is here, you will see that this W kind of brings this to the original equilibrium position, right? So let's calculate the moment, because as you see, you have this around this. You will have this force. One is this way and one is this way. So this force is kind of taking this object back to its original position, right? So this W is a restoring force. Where it brings back the object to the original position, equilibrium position, and therefore this is a stable equilibrium situation, okay? So this is important to note that even if you do it to the left, to the right, if you displace it to the right, you will see the same thing, that the W is gonna put back this object into the original, its original equilibrium situation and position. So this equilibrium is a stable equilibrium. This equilibrium state is a stable equilibrium state for this shape, okay? So now let's investigate a second shape, a second object. So in this object, we have a similar shape, but what I'm gonna do is I'm gonna put the heavy part on top. So I have a heavy part on top. Okay. So what I'm gonna have is that the center of area is here, and the center of gravity is at the top, right? So I have a force here from the center of gravity, and then another force from the center of area as FB. Yeah, let me a little bit increase the size. So it can be clearer. So we have a center of gravity that acts, say, from here. And then we have the buoyancy force that acts, say, from the center. So we have this, and then we have this force from the center of gravity. Let me again. Maybe let me zoom a little bit. So we have this from center of gravity. So this is FB, the buoyancy force, and this one is the weight of the object, okay? So what's gonna happen now? So let's see if we move this a little bit to the right, what's gonna happen to it, to this object. So here we have the center of gravity, and then the weight of that object that acts here. And then from the center, we have this buoyant force that acts this way, right? So what's going to happen here? If you look at it, if you take the moment from the center, you will see that this W is going to actually turn this down to a new position, right? So it's going to continue just falling and changing it, right? So this W is overturning couple. So this, you see an overturning couple is formed here. So this is going to be an unstable equilibrium because it's not going to come back to the original position. But what's going to happen is that this is going to overturn, right? Because of this couple that has been formed. Okay, so this is an example of an immersed body where we have kind of unstable equilibrium. Okay, so now let me go to floating bodies. So this was immersed body, and let's see what's going to be a floating body examples. So I have this, let's say I have water here. And then I have an object that is a floating object. Okay, so the center of the gravity for floating body, so the center of gravity is going to be, let's say here, at the middle of it. So we have W here, it's center of gravity. And the buoyancy is going to act in the middle of where we have water. So we have water here, so it's going to act in the middle. Okay, so what happens if I change and displace this object? Let's see. So if I displace this object, we are going to have something like this. So the center of the gravity is going to be still here, but W is down. And now, one interesting thing is, as you see, so let me show it with this. So we have water here, right? See, we have water. We don't have water, but this is like how much water is displaced, right? Something like, I think I cleaned it, but like like the Archimedes principle for finding the center where the buoyancy force impacts. And here, this much of this is inside the water, right? So this much is in water. Okay, but here the area where we have water is changed, right? We have more or less depending on the type of the and the shape, depending on the shape of the object. We have water, and so we have the center of it is going to change. So the center of it is going to come somewhere in the middle, which is here, the center of area, right? So for this shape, what do you see? You see that we have kind of a restoring force, right? Because if you take the moment, say around the center here, if you take the moment, you will have two forces. One is upward and one is here. So it's actually taking the object to this side, right? So we have a restoring force, and thus this is gonna be stable equilibrium, right? So one thing you can notice from floating bodies is that the FB, the buoyant force, the FB center may change for floating bodies, right? Because it can be that like more or less of the body of the object is going to be inside the water or the fluid. Okay, so the center of that buoyant force is going to change. And this is very important for, let me give you another example and then discuss a little bit about the implications of this. So let me give you another example. So again, we have water. For these immersed objects, immersed body, not immersed, sorry, floating body objects. So we have water here, and then I have another shape. So I have something like this. So the center of gravity is somewhere here. So we have the weight of it, so this is center of gravity. And then the buoyancy force is going to be the center of where water is, where we have kind of occupied the water, so it's going to be the center here. And then if you move this object, what are we going to see? So let me just, for this we don't have water inside it, just so you make sure you understand it. Also here we don't have water inside it. If you move this object, let's say to the right, let's see what's gonna happen. So I move this to the right. So I have the center of gravity, the weight is gonna be here. And then I have the buoyancy force, which acts here. So if you see around this point, if you take the moment around the center of gravity, you will see that you have a force that kind of tries to overturn this, right? So here we have overturning couple, and thus we have an unstable equilibrium, right? So as you see and notice, this floating body stability analysis is very important for design of boats, ship, and these marine structures, right? So as you see, if you make this object very kind of thin, you will have an unstable equilibrium. So that's very bad. You don't want this to happen, where, for example, for your ship or boat to overturn. But if you make it like wide enough, you see that because of this design, it is gonna restore back to the original shape. So this is what you want. You want to have a stable equilibrium when you design a boat or a ship, okay? And this is very important for analyzing this kind of vehicles or this kind of structures, okay? So this was just a brief overview of stability concept, and this is a very wide topic that's kind of studied in fluid mechanics, and we don't want to delve more into the details. Just this was a brief overview so you get more familiar with that, and we have one lab too that kind of goes through this in more detail. Okay, so now let me go to the next topic, which is pressure variation in a fluid with rigid body motion. So far, the fluids that we investigated, they all were at rest, right? The tank of water that we investigated was all in at rest, right? So I want to write the equation that governs the fluids that we derived before. So let me just go back to few lectures before, where we assumed that steady state condition and then drive that hydrostatic pressure. Okay, here we assume we have a fluid at rest, right? So we set A or acceleration to 0, and this is the equation we had for fluids, right? Let me see if I do it. Yes. So let me just copy this. So this is the equation we got from Newton's second law for a fluid motion. And now we assume that the A or acceleration is 0, right? But what if this acceleration is not 0? So now I want to investigate this. So this is the original equation we had. So this means that the gradient of P, as we say, this is just a definition, operator definition, that you can see it again. This means that partial P over partial X is rho A X if we have acceleration. Then partial Y over partial P over partial Y means this is just the differentiation of P with respect to Y, right? y coordinate. It's going to be rho a y, and partial p partial z means the partial differential of pressure with respect to z is gonna equal to rho a z, and we also have this component which is in the k direction or z direction. So I'm just gonna add it here, plus rho g, right? I just bring this to the right hand side, and then just write it in the z direction, which is k. Okay, so now assume we have a linear motion, a simple linear motion. So a is not 0 here. Okay, so assume that we have a tank of water like this, and then this is the coordinate system. So this is x, this is y, and this is z. And then I have water like here, like this. Okay, and then I just apply an acceleration to this. I have a linear motion and acceleration. So I give a vector a here. I have a vector a. So I just take this. I just take this object, say the whole tank of water, and then just move it this way. I give an acceleration this way. Okay. So I want to see what's going to be the shape of the interface of the water in this situation, and also the pressure gradient in my system. Okay. So again, I repeat it. I have this object, it's tank of water, and then I just apply a force, and then I move it in this direction with this acceleration. Okay. And I want to see what's going to be the behavior of this object. So I have this acceleration in this direction. I can decompose this into two acceleration in two directions. One in the y direction, I denote it as AY, and one in the z direction, and I denote that as AZ. Okay. So I have this motion is in this plane of y and z. I have an acceleration in y direction, and then I have an acceleration in the z direction, right? So let's see what happens. So the first thing I can say, I don't have any acceleration in x direction, right? So ax is 0, and thus dp over dx, partial p over partial x, is 0. And what does this mean? That means that pressure does not vary in x direction. Okay, so in this direction, the pressure is constant. It's not going to vary. Okay, so now let's go to the second one, and I'm going to use the y. Okay, this equation. So I know that partial p over partial y is going to be minus rho a y and I know that from this equation partial p over partial z is going to be minus rho g plus az. I can write dP, the total pressure gradient, as partial P over partial Y dy plus partial P over partial Z dz. And the x1 is 0, so I don't write it down. And this gives me partial P over partial Y is given here, which is what? Which is minus rho a y dy. And partial P partial Z is given here. So it's going to give me minus rho g plus az times dz. Okay. So now I want to see along a line of constant pressure. For example, the free surface. Let's say I want to find what is going to be the shape of the free surface for this, okay? I know along that line, along the free surface line or any line, dP is going to be 0, right? Along the free surface where we have, for example, if you have the free surface water, you only have say if the water even is like this, you only have the atmospheric pressure everywhere, right? It's the same here, the same pressure, atmospheric pressure here, everywhere, right? So there is not going to be any change of pressure from this point to this point, right? They both have the same pressure, which is P naught, okay? So the dP, the delta P, the pressure difference between these two is going to be 0, right? So that's the same thing here that I want to say that along a line of constant pressure, for example, free surface, dP is going to be 0. We are not going to have any change in the pressure, okay? So if dP is 0, I can set this to 0. And what I'm going to get, I'm going to get a relation between dy and dz. So let me write it down. So those are going to cancel out, but I'm going to write everything down so you see it better. Rho ay dy equals to rho g plus az dz. So rho's are going to cancel out. It doesn't matter what kind of fluid you have. You will get to this general relation between z and y. So dz of dy is going to be minus ay over g plus az. And this is a very important relation for finding a free surface of water. Okay. So here, you see, if we move this object this way, what do you expect from your intuition? How the water is gonna stand if you move it this way? You expect it to stand something like this, right? Right? So the water is going to stand something like this. This is you expect, and this is what we also got from this equation. How? So dz over dy, dz over dy, so say this is going to be let's say for not the whole system, but just a little bit of that, like here. Okay, so here you know that the pressure difference between these 2 points is going to be 0, right? Because they are all both on the free surface. Okay, so I can say that here I have dy and here I have dz. Okay, so dz over dy is going to be the tangent of this triangle here, and that slope equals to minus ay over g plus az. So ay is positive. Okay, so ay is positive, so this means that I have to have, this is gonna be a positive number, so the slope has to be negative, right? And this is what we have. So we have a negative slope here. Okay, so dz over dy is gonna be negative, and this is consistent with this equation that we have, and also our intuition that the water in this situation is gonna have this kind of free surface interface shape. Okay, so let's see, when ay is 0, what we have? When ay is 0, then this means that we're going to have dp over dy, dp over dz from this equation is going to be minus rho g plus az. Okay, and then this is going to be 0 too, and we know because ay is 0, so then this dz over dy is going to be also 0, so we are not going to have any change in the z, so we are going to have a flat surface if ay is 0. And so this means that, for example, we are just moving this object upward or downward, right? So we only have a vertical acceleration. So as you expected, this is not gonna change this theta direction, right? So it's gonna be 90 degree, and this is gonna we are gonna have a flat surface, and so this is like, it's like you have increased the gravitational, you have increased or decreased the gravitational acceleration, right? It's like you added this acceleration, virtual acceleration, to this g, to this gravitational acceleration that we have, right? So it's exactly like the effect if you are in an elevator, right? When you are in an elevator, if it goes up, so you have a positive az, right? If you are in an elevator and it goes up, you have a positive az, then it's like you have added something, increase the gravitational constant, right? You feel more weight, right? It's like your g is increased. And if the elevator goes down, right? If an elevator goes down, like your az is negative, it's like you have decreased from this gravitational constant, so you feel lighter, right? So if it goes up, you feel heavier, and if it goes down, you feel lighter. And this is the same effect here for the water. If you move it vertically, up or down, it's like with some acceleration, it's like you have added to these gravitational constant or decrease from the gravitational constant, okay? This is just to give you an intuition. And for a free falling fluid, so if you have a free fall, for a free falling fluid, when you have a free fall, it means that this AZ is gonna equal to what? It's gonna equal to minus G, right? Because AZ is in the positive direction and G is the negative direction. So minus AZ equals to G. So AZ equals to minus G. And thus, this sum here is gonna be 0. And so dP over dZ is gonna be 0. What does that mean? This is a very interesting result. This means that if you have a free fall and your acceleration, you just let this tank like fall from some, I don't know, height, okay? With the acceleration equals to minus G, okay? Then there would not be any pressure gradient. dP over dZ in this fluid is going to be 0. What does that mean? That implies that the whole pressure gradient that we learned so far, the vertical pressure gradient in fluid, in this water, these hydrostatic pressure forces that we all talked about, are all due to this gravitational force, due to this gravity. And this is this gravity that creates all these pressure differences between the bottom and the top of the tank, right? So if you just let this object free fall, there will be no pressure gradient. So if you have some water that is free falling, then there will be no pressure gradient between top H1 and H2 of that, okay? So this is what this means. And also, in space where we don't have any gravity, there will be no hydrostatic pressure gradient as well, right? As something like this rho GH that we learned so far, this is all because of this G or gravity or gamma H, the specific weight, okay? So this is a very important point for you to consider, especially for giving you intuition of where these hydrostatic pressure force comes and what happens if you have a rigid body motion in fluid. So this is again the equation that we had and we used, okay? So now let me solve an example for this short example for this rigid body motion in fluids. So imagine we have a moving vehicle, and that question asks to A, determine the pressure at the transducer and B, maximum acceleration before the fuel level drops below the transducer. Okay, so here we have a vehicle that moves and in this direction, in the Y direction, say, okay. And this is the fuel tank, okay. We have some gas here, some fuel or gas. And this is the transducer where this fuel is kind of transmitted to the engine, okay? And so we want to calculate two things. First, we want to see what is gonna be the pressure at the transducer, okay? And then the second thing is the maximum acceleration that before the fuel level drops below the transducer. So we want to see at some level, at some point, if the acceleration is too high, then we are going to have a shape like this, right? Because this is going to move this way. And so the fuel is going to go below the transducer, and that can cause some problems, okay? So this is something we want to calculate, what is going to be the maximum acceleration where this is going to happen. So this can help us to design this transducer in a right position so that we see designed maximum acceleration of the vehicle to match with each other, so that never this fuel level drops below that transducer. Okay. So let me get started. I want to write the equations for here. This is the same similar equation that we have. So dz over dy equals to minus ay over g plus az. Okay, so we don't have a vertical acceleration. Here is all horizontal acceleration, so this term is going to be 0. So this equals to minus ay over g. And so this is, if this is z1, let me write it down again so you see it better. So this is z1. So let's imagine this triangle here. I'm writing it for this triangle. So for this triangle, I first want to find z1. So that's the first thing I want to find. And then I want to calculate the pressure at the transducer, okay? So let's imagine this triangle. So from that triangle, I can say that minus z1 over 0.75 is gonna be equal to minus ay over g. Okay, so z1 is gonna be 0.75 meter times ay over g. Okay, so I have this z1, and now I can calculate the pressure at the transducer. So the pressure at the transducer is going to be simply calculated with this rho gh of water on top of that, rho water. So it's going to be, no, it's not water, sorry, it's fuel or gas, and I haven't written it. I had to write it here. The rho of fuel is 750 kilogram per meter cube. It's less dense than the water. So we have rho fuel here, and then HF the fuel here on top of that. So it's going to be 750 times 9.81 Newton per meter cube times HF, which is gonna be this height here. Let me just zoom so you better see it. This is Z1. From here to here is Z1. From here to here is Z1. And then from here to here, this green one is gonna be 0.5 minus Z1, right? Because this is the whole thing is 0.5. So this green one is gonna be 0.5 minus Z1. So let me write it down. 0.5 minus Z1. What is Z1? Z1, I just write it from here. It is gonna be 0.75 AY over G, which equals to 368 kilopascal minus 5.52 AY over G kilopascal. Okay. So if the value of AY is given, we can just evaluate it. So I just wrote it based on AY. Okay. So this is for A. So let me write it answer. And for B, so for B, it says maximum acceleration before the fuel level drops below the transducer. So let's see what happens. If we want to find what is going to be the maximum acceleration where this goes below this, so either you can set Z1 to be 0.5, that's one way, or another way is you say once this goes here, then the pressure at the transducer is going to be 0, right? Or P naught, which we can assume it's 0. Atmospheric pressure, right? So we don't have any hydrostatic pressure, okay? So AY max happens when P is 0. So 368 kilopascal should equal to 552 times AY over G, and thus AY is gonna be 6.54 meter over second square. This is one way, or the other way, you just set this to 0.5 and you should get the same thing here, okay? So this is going to be the maximum acceleration before this fuel drops below the transducer. So it means if you go with a higher acceleration than 6.54 meter per second square, then the fuel is going to drop below the transducer, and thus your engine will not have fuel, and so you cannot move faster, okay? So this is very important for design of these kind of also the design of these fuel tanks, okay? So this was the end of chapter 2, and after this, in the next session, I'm going to start chapter 3, where we start Bernoulli equation. So just a brief overview, we discussed stability concept here. We talked about stable equilibrium, in which it is when the object displaced, when it's displaced, it returns to its equilibrium position, and then unstable equilibrium, where what it means is that when the object is displaced, it's gonna move to a new equilibrium position. So we show some examples of that for immersed bodies and floating bodies. And then we talked about pressure variation in a fluid with rigid body motion. So we derived the formula. We had this formula before, but we just assumed that acceleration is not zero. And so we came up with this formula for if you have a two-dimensional acceleration, a linear motion in y and z plane, 2D plane. And this was the formula for the interface shape. We can use it or any line of constant pressure. So the constant pressures for this fluid is going to all look like this. Just so you know, it's going to all look like this. Okay, so these are the constant pressures. And when you want to calculate the gradient, it's going to be like this. So this is where we have the gradient. Okay. And we said if we don't have a horizontal acceleration, only have a vertical acceleration, it's like we increase or decrease the gravitational constant like when you are on an elevator. Okay, and for a free-falling fluid, we don't have any pressure gradient. Okay, and finally, we solved an example for this moving vehicle where we kind of calculated the maximum acceleration before the fuel level drops below the transducer. Okay, thank you, everyone.